So what I'm going to talk about today is in chapter 5, what are called inner product spaces. And so what's an example? So let me start with an example of an inner product. Which, if you took Calc 3 or vector calculus, you certainly would have seen, which is in Calc 3 is sometimes called the dot product and sometimes called the scalar product. So if you have two vectors that say v is the vector x1, x2, v1, or let me use coordinates x and y, maybe just to make it a little bit easier. If v1 has coordinates x1, y1, and v2 has coordinates x2, y2, the standard inner product, which we write v1, v2 like this, is x1, x2 plus y1, y2. So if you had, for example, v1 is the vector 2, 3, and v2 is the vector minus 7, 5, then v1, v2, that inner product, would be 2 times minus 7 plus 3 times 5, which is 1. It's a number. So, or if you had the vectors v1 equal 2, 3, and v2 is the vector 3 minus 2, then their inner product or dot product would be 2 times 3 plus 3 times minus 2, which is 0. And if you were actually going to graph these in the plane, the vector 2, 3 is there. And the vector 3 minus 2 is there. And in fact, if you look carefully or draw it carefully, these vectors are perpendicular. And for the ordinary scalar product, non-zero vectors v1, v2 are perpendicular if and only if their inner product or dot product is 0. So again, if you took 226 vector calculus, you're very, very familiar with this. Also, when you have the dot product or the inner product, we can define the length of a vector. We never did this before. We've been dealing with vectors, but we never talked about the length. So for example, if you have the vector v, which is 3, 2, then what is defined to be the length of v is you take the inner product of the vector with itself and the square root of that. That's equal to, in this case, what's the inner product of v with v? It's 3 times 3 plus 2 times 2, or 13. So the length of v would be the square root of 13. By the way, why is this exactly natural? Suppose you have the vector xy in the plane. So here's the vector xy. That's v. This is x, this is y. What is the inner product of v with itself? You take x times x plus y times y. That's x squared plus y squared. What is the length of the vector v? Well, by the Pythagorean theorem, the length of v which we write as V usually with absolute value signs around it, is the square root of x squared plus y squared. That's the Pythagorean theorem, which is exactly the square root of the inner product of V with itself. So with the ordinary inner product, we have a way to talk about the length of vectors. We have a way to talk about when two vectors are perpendicular or not. And we'll also show we have a way to talk about the angle between two vectors. So if we have a vector v1 and a vector v2, we prove a theorem that says the inner product of v1 and v2 is equal to the length of v1 times the length of v2 times the cosine of the angle between them. So if you want to know this angle theta, the cosine of theta is the inner product of v1 and v2 divided by the length of v1 times the length of v2. Or if you like, you can say theta is the arc cosine or the inverse cosine of this. We only talk about the length of the angle between two vectors when the two vectors are non-zero. If vectors are non-zero, the lengths are positive. So these are positive numbers in the denominator. It's never zero, so I can always do this division. Okay, so this is just the most important example of an inner product. This is the inner product in two-dimensional space. In R3, the standard inner product is defined as follows. It's just the natural thing. And again, you use this in vector calculus all the time. If V1 has coordinates x1, y1, z1, and V2 has coordinates x2, y2, z2, then the inner product of V1 and V2, you just take the sum of the products of the coordinates, x1, x2, plus y1, y2, plus z1, z2. And if we have non-zero vectors, V1 and V2, V1 and V2 are perpendicular if the inner product is zero. The length of the vector V is the square root of the inner product of the vector with itself, which if V is coordinates x, y, and z, this is exactly the square root of x squared plus y squared plus z squared, which is how you define the length of a vector in Euclidean space to begin with. The angle theta between vectors is given by the cosine of theta is the inner product of the two vectors divided by their lengths. And this, in fact, immediately implies the perpendicular condition, because two vectors are perpendicular, so V1 perpendicular to V2, if and only if the angle between them is pi over 2 radians, which means the cosine of the angle is 0. So if the inner product is 0, the cosine is 0, so the angle between the vectors is pi over 2, and they're perpendicular. And conversely, if the vectors are perpendicular, the cosine is 0, which means the inner product has to be 0. So this is just to put the inner product into the setting that should be very natural. Okay. Any questions about this? This is really just what you might call a kind of warm-up. It's just to practice to get us started.
On the second line where you put inside of the length, is that just the formula?
Yeah, this is the formula for the length of a vector. You take the inner product of the vector with itself and the square root of that.
Okay, you just know, you just do a notation differently on the bottom.
Here,
No, a little below.
here.
Yeah, that's just a different notation saying the same thing.
Well, here I'm talking about the length of a vector, which I write with just absolute value signs around the vector. And here I'm talking about the cosine of the angle between two vectors. So this is one thing. So here I have three different statements. 1, 2, 3. Right? Two vectors are perpendicular if the inner product of them is 0. The length of a vector, absolute value v, is the square root of the inner product of the vector with itself. And the angle theta between vectors is given by the formula that the cosine of theta is the inner product of the vectors divided by the product of their lengths. So those are three separate statements.
And on the bottom in the middle, it says theta equals pi over 2.
So here, this symbol means perpendicular, right? So that means perpendicular. So what does it mean for two vectors to be perpendicular? It means the angle between them. Before you learn calculus or pre-calculus, you would have said the angle was 90 degrees, but we never use degrees to measure angles. We use a radians, so pi over 2 radians. So V1 is perpendicular to V2, means, or if and only if, the angle theta between them is pi over 2 radians, and theta equal pi over 2 is the same as cosine theta equals 0. Right? So this is not calculus, this is pre-calculus, right? This is what it means for two vectors to be perpendicular. Two lines are perpendicular if the angle between them is pi over 2. Okay, so this is kind of warm up, and now I have to give you the definition of an inner product. So we have a real vector space, which means a vector space over the field of real numbers. That is, we could have been using complex numbers for our field, or we didn't, but this is now just for vector spaces over the real numbers. And an inner product, the vector space V. And inner product on V is a real valued function on V cross V. This means this is a set of all pairs of vectors, VW, where V and W are vectors in V. So this is all ordered pairs of V and W, and we're interested in a function on V cross V such that the following properties are satisfied. So the first is f of VW is defined. If the first coordinate, the first argument is a sum of two vectors, f of v plus v prime comma w, this is going to be, in fact, maybe I'll just not even use f, it's just a function, but I'll just denote the function by this parentheses around it. So v plus v prime comma w is vw plus v prime w. Second, cv comma w, c is a scalar, is c times vw. So this is just the same as saying if we fix W, this is a linear transformation from V into R. Right? The third property is that if I have V comma W plus W prime, this is VW plus VW prime. And the final condition is that V comma CW, I can take the scalar out from the second coordinate as C times VW. So this scalar, this inner product, V comma W, has to satisfy these four properties for all vectors V, V prime, W, W prime, and all scalars C. And this is a function that has these properties is called bilinear. Because it's like a linear function, but in two variables, so it's bilinear. And we say that this is positive definite if the inner product of every vector with itself, it's a real number, but it's always positive for all non-zero vectors V. And we say that these inner product, this function is symmetric if the inner product of V with W is the same as the inner product of W with V for all vectors V and W in the vector space. So an inner product on a vector space is a function that assigns a number to every pair of vectors. And that function has the following very nice properties. It's symmetric. The inner product of V and W equals the inner product of W and V. It's positive definite. The inner product of any non-zero vector with itself is positive. And it is bilinear. That means if you fix the second coordinate and look at this inner product, it's just as a function of the first coordinate, it's linear. And if you fix the first coordinate and you look at this inner product just as a function of the second variable, it's also a linear transformation. It's linear. So that's what an inner product is. And the examples, the standard examples are the inner products in R2 and R3 that we just saw. Right? So this inner product, or this function, satisfies all the properties we just discussed. And similarly for the standard inner product in R3. And what is often called a Euclidean space is a finite dimensional vector space over the field of real numbers with an inner product. So on Rn, the standard inner product is defined as follows. If V1, or I'll use the notation that's in the notes, if V is the vector x1, x2 down to xn, and W is the vector y1, y2 down to yn, then we define the inner product of V and W to be just the sum of the corresponding coordinates, x1, y1, plus x2, y2, plus x3, y3, up to xn, yn. Or in sigma notation, this is summation. I goes from 1 up to n, xi, yi. So if you have v is 3 minus 5, 2, and w is 7, 1 minus 9, then the inner product of v and w is 3 times 7 plus minus 5 times 1 plus 2 times minus 18. That's 21 minus 5 minus 36 is minus 20, I think. That's the inner product of those two vectors. And it's easy to check that this inner product has all of the properties of an inner product. It's bilinear, it's symmetric, and it's positive definite. For example, if this is the vector v, what's the inner product of v with itself? It's 3 times 3 plus minus 5 times minus 5 plus 2 times 2, 9 plus 25 plus 4. It's 38. Positive number. Let's see. So recall a simple function which is called the Kronecker delta. Delta ij, it's defined to be 1 if I equals j and 0 if I is different from j. And in Rn, we have the standard basis E1, which is 1 and then all zeros. E2, each of these vectors is going to have exactly 1, 1, and every other coordinate 0. In E2, the 1's in the second place. In E3, the 1's in the third place, and so forth, up to En, where the 1 is in the final place, n, right? And if you take, for any one of these vectors, the inner product of the vector with itself is going to be, so what's the vector? The vector EI is all zeros except a 1 in the ith coordinate. So EI inner product with EI, you're taking the sum of the squares of the coordinates. 0 squared plus 0 squared plus 0 squared. In the ith place, you get a 1 squared, and then all zeros. This is just 1. So the inner product of EI with itself is 1. And the inner product of EI and EJ, for I different from J, you're going to have 0 times 0 plus 0 times 0. When you get to the ith place, you're going to get a 1, but the ith coordinate in EJ is 0. When you get to the jth coordinate, you get a 0 times 1, which is 0. Everything is 0. You get 0. So for the standard basis, the inner product of two basis vectors, EI and EJ, is exactly the Kronecker delta. If I equals J, this is 1. If I is different from J, it's 0. Okay. Any question about this? This is the inner product. Now, There are many different inner products. We're using the standard inner product in Rn, but let's look at another example, which is important in calculus. Suppose we let V be the space I sometimes call C01. This is all continuous functions f defined on the unit interval, right? So 0, 1, this is just the graph y equals f of x. So a vector in this vector space is just a function. And I can define an inner product by integration. We define the inner product of two functions f and g to be the integral from 0 to 1 of f of x, g of x, dx. So to every pair of continuous functions on the interval from 0 to 1, I integrate their product, that's some real number. That's how I define the inner product. How can I show this is an inner product? Well, suppose, for example, I take some linear combination of functions, C1F1 plus C2F2, inner product with G. So that's the integral from 0 to 1, C1F1 plus C2F2 times G of x times G of x dx. But by the standard properties of integrals, this is C1, the integral from 0 to 1 of f1 of x, g of x dx, plus C2, the integral from 0 to 1, f2 of x, g of x dx. That's C1 times the inner product of f1 and g, plus C2 times the inner product of f2 and g. So the first two properties of inner product are satisfied. If I take the inner product of g and f, this is the integral from 0 to 1 of g of x, f of x dx. This is the same as the inner product from 0 to 1. G of x, f of x is the same as f of x, g of x. So this is the inner product of f and g. So this inner product is symmetric. And if I take the inner product of a function with itself, if f is not identically 0, this is the integral from 0 to 1 of f of x times f of x dx. That's the integral from 0 to 1 of f squared of x dx. This is a positive function. It's never negative. It's always greater than or equal to 0. It's greater than 0 somewhere because the function is continuous, which means it's greater than 0 on some, at least on some little interval. So this is positive. So this is positive definite. So this is another example, or a new example, but a really interesting example of an inner product on a natural vector space. Given an inner product, we define the length of a vector v by, sometimes I use double brackets, sometimes single bracket. That's the length of v. You take the inner product of v with itself, take the square root, and that's v. And of course, this is equal to 0 if and only if v is the 0 vector. Because the inner product, every inner product is positive definite. If v is 0, the inner product is 0, and the square root of 0 is 0. But if v is not 0, then this inner product is positive, because an inner product is positive definite. And the square root of a positive number is positive. And a unit vector is a vector of length 1. So in Rn, if I take the vector EI, be the vector where all the coordinates are 0 except for a single one, which is 1, the inner product of EI with itself is 0 squared plus 1 squared, and then 0 squareds. It's equal to 1. So the length of EI is square root of 1, which is 1. So the standard basis in Rn consists of unit vectors. If W is a vector not equal to 0, then we know that the length of W is positive. If we let V be W divided by its length, then the length of V is the length of W divided by the length of W. But you can take a scalar outside. This is 1 over the length of W times the length of W. These cancel. This is 1. So V is we call it a unit vector in the direction of W. So here we have V, here we have W, and if you divide it by its length, you get a unit vector of length 1, but pointing in exactly the same direction. And there's some very nice geometrical properties of that connect inner products and lengths. So let's see. So given an inner product, right, like this, right, VW, we get a length. So the inner product divides the length of a vector. The length of V is the inner product of the vector with itself, square root. But it's also true that from the length, we can recompute, we can recover the inner product, because we have the following identity, which is called the polarization identity. For any vectors V1 and V2, the inner product of V1 and V2 can be defined in terms of the length. This is 1/4 the length of V1 plus V2 squared minus 1/4 times the length of V1 minus V2 squared. So if you know the lengths of vectors, you can get an inner product. And the proof goes as follows. Recall, the length of a vector V is the square root of the inner product of the vector with itself. So the length of a vector squared is just the inner product of a vector with itself. So if I take V1 plus V2 squared, that's the inner product of V1 plus V2 with V1 plus V2. We take the inner product of this vector with itself. But now, using bilinearity, we can expand this. This is V1 times V1 plus V2 plus V2, inner product of V2 with V1 plus V2. And I can expand this. This is V1 V1 plus V1 V2 plus V2 V1 plus V2 V2. And V1 inner product with V2 is the same as V2 inner product with V1. So this is the length of V1 squared plus 2 times the inner product of V1 and V2 plus the length of V2 squared. And in the same way, if I take the inner product of V1 minus V2, or I take the length squared of V1 minus V2, I can replace V2 by minus V1. I would get V1 squared minus 2 V1 V2 plus V2 squared. So if I subtract this minus this, these cancel. So the length of V1 plus V2 squared minus the length of V1 minus V2 squared. This minus this is 0. This minus this is 4 times the inner product of V1, V2. This minus this is 0. So if I divide by 4, I get the inner product. And that is this very nice proof of the polarization identity. Let's see. There's one more fundamental thing I want to prove. And let me just see where it is. Oh, there it is. So this is in section 5.4. There are two inequalities involving vectors in inner product spaces. Bessel's inequality and the Cauchy-Schwarz inequality. So we need a preliminary definition. So recall, we say that vectors v1 and v2 are perpendicular or orthogonal. Orthogonal is just another word for perpendicular. If non-zero vectors, if their inner product is 0. And unit vectors, a unit vector v has length 1. A set of vectors, say E1, E2, up to En, is orthogonal if EI, EJ is 0 for all I different from J. Or equivalently, a set of vectors is orthogonal if every pair of them is perpendicular. Every two different ones are perpendicular to each other. So in three-dimensional space, if I take vectors along the x, y, and z coordinates every two of them, every pair of them is perpendicular. So these are an orthogonal set of vectors, and an orthogonal set of vectors is called orthonormal if it's orthogonal and the length of each vector is 1. So an orthonormal set of vectors is a set of vectors that are pairwise orthogonal or perpendicular, and every vector has length 1. And the standard basis, E1 up to En in Rn, is orthonormal, right? That's the basis where each vector consists of all zeros except for a single coordinate equal to 1. And so that's very nice, an orthonormal basis. And in fact, there's a method given any basis for a vector space, a finite dimensional vector space with an inner product, to build from it an orthonormal basis. So orthonormal, let me just say, orthonormal bases for vector spaces are good or nice, something that's easy to work with. And the standard example is this in Rn. So Bessel's inequality says the following. That E1, E2 up to En be an orthonormal set of vectors in some vector space V. That V be in V. Then if I take the inner product of the vector V with the basis vector EI, I call this C sub I. This is called the Fourier coefficient. Of V with respect to this vector EI. So if you study more advanced calculus, you learn about Fourier series. But the Fourier coefficient can be defined whenever you have an inner product space, an orthonormal set of vectors. You take a vector V and its inner product with EI is called the ith Fourier coefficient. And Bessel's inequality says if you take the sum, I going from 1 up to N, of the sum of squares of the Fourier coefficients, that's always bounded above by the length of the vector V squared. So this is Bessel's inequality. And the proof is a calculation. Maybe it's a little bit long. So proof. Let me take a whole sheet of paper for this. So we have E1 up to En, orthonormal, V is a vector in V, C sub I is the inner product of V with the coordinate vector E sub I. And let me define a new vector V prime, which is going to be the vector V minus the sum of C sub I times the vector E sub I going from 1 up to N. So E1 up to En is a set of vectors. V is a vector. Ci is a scalar. I take the inner product of V with Ei. I look at this linear combination of E1 up to En. I multiply Ei by the scalar Ci. I add and look at V minus that. And that's my vector V prime. Now, I'm going to take the inner product of V prime with itself. The inner product of a vector with itself is always greater than or equal to 0. It's 0 if V prime is the 0 vector, otherwise it's positive. So the vector V prime with itself, the inner product, this is V. This is V prime. So it's V minus summation Ci Ei. I goes from 1 up to N. Inner product with the same thing. V minus summation I goes from 1 up to N. Let me use a different index here. J goes from 1 up to N. Cj Ej. That's the inner product of V with itself. Now I can expand this using this bilinearity. This is V inner product with this. Minus summation Ciei. I goes from 1 up to N. Inner product with this. And then I can again expand this by bilinearity. This is the inner product of V with V minus the inner product of V with summation Cj Ej. J goes from 1 up to N. Minus this inner product with V, summation Ci Ei, inner product with V. I goes from 1 up to N. Minus times minus is plus the inner product of summation Ci Ei. I goes from 1 to N with summation Cj Ej. J goes from 1 to N. I can continue to expand this. This is the inner product of V with V minus by the bilinearity summation J goes from 1 to N V comma Cj Ej. I can take the Cj outside. I'm just going to be considering real vector spaces. Minus summation I goes from 1 to N Ci times the inner product of Eiv. Plus now I have a double sum. I goes from 1 to N, J goes from 1 to N, Ci Cj Ei Ej. That's what I have. If you're following in the book, this is on page 290. Now, Ei Ej, the inner product of Ei and Ej, this is a set of orthonormal vectors. So this is 0 unless I equals j. And when I does equal j, it's equal to 1. So this is just delta ij, the Kronecker delta. This is 0 unless I equals j. And when I equals j, it's 1. So this term is really just summation. I goes from 1 up to n, c sub I squared. And the inner product of, here, let me just make this an I. So Make it easier. I. The inner product of V with EI is the same as the inner product of EI with V. So these two terms are the same. So what I get here is V comma V, that's the length of V squared, minus 2 times the sum C sub I times the inner product of V with EI. I goes from 1 up to N, plus summation C sub I squared. I goes from 1 up to N. But the inner product of V with EI, this was defined to be CI. So what we actually have over here is 2 times the length of V squared minus 2 times summation CI squared, I goes from 1 up to N, plus summation CI squared, I goes from 1 up to N. These are the same. This is the length of V squared minus summation CI squared, I goes from 1 up to N. And all of this is greater than or equal to 0, which means if I take this on the other side, the sum of the squares of the Fourier coefficients is less than or equal to the norm of V. And that's what I wanted to prove. That's the proof of Bessel's inequality. And from that, I want to prove the Cauchy-Schwarz inequality, which is one of the most important inequalities in mathematics. So let me just state the Cauchy-Schwarz inequality. It says for any vectors U and V in my inner product space, the inner product of U and V in absolute value is less than or equal to the length of U times the length of V. This is Cauchy-Schwarz. And just as an example, what does this say in R2 with the standard inner product? So if U is x1, y1, and V is x2, y2, the inner product is x1, x2 plus y1, y2. The length of U, well, let me square both sides just to get rid of squares. So this squared, the length of U squared is x1 plus y1, x1 squared plus y1 squared, and the length of V is x2 squared plus y2 squared. So this very interesting inequality for real numbers, for any numbers, x1, x2, y1, y2, we have this inequality. This expression is less than the sum of the squares here and the times the sum of the squares there. That is Cauchy-Schwarz. So let me try to prove that. And the proof uses some elementary facts from high school algebra, quadratic equations. So suppose we want to solve AT squared plus BT plus C equals 0, a quadratic equation. So you know the quadratic formula. The answer, the solution T, is minus B plus or minus the square root of B squared minus 4AC over 2A. And B squared minus 4AC is what's called the discriminant of the quadratic equation. And the number of real solutions of the equation is what? Well, if B squared minus 4AC is positive, there are 2 square roots. So there are 2 solutions if b squared minus 4ac is positive. If b squared minus 4ac is 0, there's just one solution. And if b squared minus 4ac is negative, there's no real number that's the square root of a negative number. So there's 0 solutions if b squared minus 4ac is less than 0. Let's see, there's one other thing we can say. The function f of t equals at squared plus bt plus c equals 0. So the graph, so if a is positive, the graph's a parabola going up. If there's no solution, then the graph can never cross the x-axis. It has to be above the x-axis. If a is negative and there's no solution, the graph always has to be below the x-axis. Because if a is positive, this goes to infinity. If a is negative, it goes to negative infinity. Oh, excuse me 1 second. Okay. Maybe I'll continue this on Wednesday. There are only 1 or 2 things that I really want to do where we are. So let me just sort of summarize. We have inner product spaces. And so we know about length of vectors. From the Cauchy-Schwarz inequality, it says the inner product of u and v in absolute value is at most the length of u times the length of v. So the inner product of u and v divided by the length of u times the length of v is at most 1, between 1 and 0. This is an absolute value. And we can define the angle between 2 vectors, the cosine of theta. Cosine of theta in absolute value, cosine theta is between -1 and +1. So the absolute value of cosine theta is between 0 and 1. We define this to be the cosine of theta, and we now have the absolute, we now know the angle between vectors. And so we already talked a little bit on last week about eigenvalues and eigenvectors for 2 by 2 matrices. And this tells us a little bit about inner products, the length of vectors, angles between vectors, when vectors are perpendicular. And there's one other result I'm going to state that tells us something about when you know that matrices have eigenvectors and eigenvalues. But that really takes a little bit more time than I have right now. So I think we're going to end right now. And I will have, I might add an extra lecture, but if you can at an odd time, if you can't attend it, that's no big deal. I will make sure that I video it and record it, and I'll go over the exam at that point. But on Wednesday, we'll talk more about inner product spaces and eigenvalues and eigenvectors. Anything before we quit for the morning? If not,